So today we're going to be talking about debugging neural networks for NLP. And I think this is very timely, especially because everybody is doing your assignment right now and probably in the process of debugging your neural networks. So for text classification, it's actually a little bit easier. Than, for example, something like structured prediction or sequence models or something. But some of this will be useful immediately now in your text classification stuff, and some of it will be useful down the road when you do more complicated outputs, prediction of more complicated outputs. And one of the reasons why debugging is so difficult in neural networks compared to other things, I guess there's a couple reasons, but one of the biggest reasons is because tuning is paramount. So everything in your model is a hyperparameter that in your results may depend on it. So for example, network size and depth, this is a hyperparameter. Small model variations, like how big do you make your model, how many layers, etc. Do you use convolutions or recurrent neural networks? That's a big model variation, but that's another thing. How do you create your mini batches? Do you create your mini batches by sorting everything first or not sorting everything first? How do you shuffle your data? Can have an effect on the results. The optimizer and the learning rate can have an effect on the results. Also, I forgot to list it here, but how you initialize your parameters. Remember, every time we randomly initialize our parameters, this can have an effect on the results. So because the models are complicated and opaque, debugging can be quite difficult. However, there is some good news. And the good news is, while there are lots of different problems that you might encounter while doing this, it's kind of easy. It's possible to understand your problem and be able to whittle down the reasons why you're having a problem. And this is kind of key to being able to effectively debug your models. And a typical situation you might encounter is, you've implemented a nice model, you've looked at the code and it looks okay, you can't find any obvious bugs, but your accuracy on the test set is bad. I think everybody has experienced this at some point. And the problem is, you're going all the way from code to this without having any intermediate steps that you can look at. So what do you do? And the first key to this is understanding the potential causes for problems with your model. And we can separate these into several different types. The first type is training time problems. For example, we can have lack of model capacity, inability to train the model properly for various reasons, a bug at training time where you're accidentally doing something that you didn't expect you were doing. We can also have test time bugs. This is something that isn't quite as much of a problem for text classification, such as a disconnect, but it is a problem for things like structured prediction. And we can have things like disconnects between test time and, training time and test time. Or we could have like a failure of the search algorithm, etc. We could also have problems with overfitting. So overfitting is a major cause of us not doing well on the test set. And we can also have a mismatch between the optimized function and what we're actually evaluating. So this is great because we actually had a question on Piazza precisely about this. I'll go into detail about this as well. So for the rest of the time here, I'm going to be talking about each of these problems individually, how to identify them, and how to debug them, and how to fix them. And the first one, as I said, was training time problems. So how do we identify training time problems? Basically, what we want to do is training time, if you remember, is trying to decrease our loss function. That's the whole goal of training. It's not trying to optimize accuracy. It's not trying to generate nice outputs. It's trying to minimize our loss. And so what we can do is we can look at the loss function calculated on the training set. We don't even need to look at the development set and say, is the loss function going down? And especially, is it going down basically to 0 if we run training for long enough on a small data set? And if not, you have a training problem. So the nice thing about this is now we don't even need to look at the test set. We can just look at the training set. We don't even need to look at accuracy. We can just look at the loss function. And there's a number of reasons why this might not happen. The first thing you can do, again, in this case, we have 200,000 training examples or something like that in our training set. You can actually reduce that to 1,000 or something. Just subsample it down to 1,000 and make sure your model can fit those 1,000 and reduce the loss to 0 on that 1,000. If it can't do that, your model might be too weak. So for example, you might have a really small hidden layer size. Let's say you set your hidden layer size to 16 with a single layer. It might be that that's just not enough capacity to give your model to learn what it needs to have. The size of the model depends on the task. So like what kind of task you're handling, what kind of architecture you're using will determine the necessary size of the model. But like, let's say we're talking about RNNs and we're talking about a language modeling task. In this task, my experience is that you need at least a hidden layer size of about 512. Anything less than this and you get much worse accuracy on any decently sized set. Larger than this, of course, you can do better, but this is one kind of threshold that you might want to think about. For things like language analysis tasks, including text classification, actually it's very common that you don't need quite as large a model. For example, the size of 128 or so may do. Does anyone have an idea why this is the case? Like why for predicting the next word in a language model, do we need a larger model? But for things like part of speech tagging or maybe text classification, we can get away with a smaller model. Size of the classes you're trying to predict, and that's exactly correct. So in the case of like text classification, the number of classes we're predicting might be 5, or it might be, what is it in the homework, 12 or something like that? 16. So if this is the case, basically we're taking a huge high dimensional space and reducing it down into 16 classes. So what we want to do is basically get rid of the unnecessary information and use that to predict what we need as the output. But for language modeling, we have 10,000 or 100,000 words that we want to be predicting. We also need to maintain information over long time periods in order to be able to make this prediction correctly. So because of this, we need more model capacity to do so. In addition, multiple layers are often better. So if you have a single layer model, kind of the types of transformations that it can do with only a single linear transform in nonlinearity. I mean, if you make the model arbitrarily large, you can do any transformation that you want. But given a reasonable size of a model, it's often easier to express this with 4 layers of size 256 instead of 1 layer of size 1024, because as you go up the layers, you gradually get more abstract features, etc. Also, for long sequences, for example, if you're doing a character-based language modeling task, it's very common that you need a larger model as well. And the reason for this is, for a word-based language modeling task, you need to remember what words you've seen. But for a character-based language modeling task, for example, you need to first transform the characters into concepts, essentially. You take the characters, you identify which word you're looking at, and you transform it into kind of a higher level concept, and then you reason over those concepts. So essentially, you're increasing the amount of processing you need to do. And it's similar for, I'll get to that. It's similar for document level tasks. So in document level tasks, you need to remember things over a longer time period. You might want to take previous sentences and kind of abstract them into kind of higher level concepts. And because of this, you tend to need more model capacity. Question?
So if the training loss does not decrease to 0, why would that be indicative that the model might be too weak? Because we are just training on a very small number of samples, and even a small model could probably do that.
So if the training loss decreases to 0, why is that indicative of not having enough model capacity? If you're just training on a small number of samples, that is the case, that probably even a small model will be able to fit them. This is actually more on, specifically for this is actually more when you're training on full data sets. Another thing you might observe is that a smaller model will decrease to 0 eventually, but a larger model will decrease much more quickly. And this can also be indicative of not having enough model capacity. So if the loss goes down much faster for a larger model, then this can be indicative that you need to be using a larger model. Any other questions? Okay. So one thing you do need to be careful of, though, is if you make a very deep models can work well, but you do need to be careful of them. The reason why you need to be careful of them is because of vanishing gradients, which we talked about in the RNN-based models. So we have a standard RNN, and what is our solution to the standard RNN having vanishing gradients? The LSTM, yeah, LSTM or GRU or something like that, right? Some sort of model that adds an additive connection between the previous inputs that we had. And when we're using a deep model, there are similar solutions to this, except between layers. One example of this is residual connections. And residual connections, basically what they do is they have transformation layers with, linear transforms, nonlinearity, linear transform, nonlinearity, but they also add the previous input to this transform model. So basically, what this model is doing is it's trying to learn how you want to change the input from layer to layer, as opposed to learning like what you actually want the output to be. So this is kind of the equivalent. So if you think of an LSTM as having additive connections between timestamps or left to right, residual connections are having additive connections between layers, or like top to bottom, or bottom to top. Now for GRUs, the equivalent of GRUs in the kind of bottom to top space is highway networks, and highway networks are very similar to GRUs. And if you remember GRUs, basically what they had was they had a gating function where you take some sort of transformation and multiply it by the gate, and then the previous input and multiply it by 1 minus the gate. So this is essentially what a highway network is doing, but it's doing it from layer to layer. So these are two options. I think virtually all big models that people use for language modeling or whatever, like BERT, et cetera, includes this sort of residual connection in it. I think this is more popular than highway networks, but highway networks also seem like a good choice as well that you might want to try. Okay, so this is about increasing model capacity. Another problem that you can have that can cause you to not get a loss of 0, even on a very small training data set, is problems with optimization. If increasing the model size doesn't help, you may have an optimization problem, and possible causes can include a bad optimizer or a bad learning rate or bad initialization. Or something like a bad mini batching strategy. So I'll go through each one of these one at a time. Some of this is just reminders from previous classes where I've already talked about things, but I'll talk about them specifically from the point of view of debugging. So for optimizers, if you remember, we talked about things like SGD, SGD with momentum, Addigrad, Atom, and many others. And all of these are options. All of these, or at least SGD, you can prove that this will be able to converge to some solution. I don't think you can prove that it will converge to a solution that minimizes the training loss, but with a sufficiently large network, it should be able to do so. But there is one condition that you need to be very careful about your learning rate with respect to SGD in order to guarantee that it will converge to something. For the others adaptively modify the learning rate, so you need to be a little bit less careful about the learning rate, but it still is a very important parameter. So with respect to learning rate, the problems with learning rate is if the learning rate is too low, you will not learn or learn very slowly. And if it's too high, you might learn for a while, but then without the loss decreasing all the way to 0, you may fluctuate around and get a non-zero loss that just never converges. So a common strategy is to start from an initial learning rate, which is a little bit higher, and gradually decrease it. In fact, this is essentially built into optimizers like Atom and Adigrad. So they start out with a high learning rate and gradually decrease it and decrease it. For something like SGD, you need to do this essentially manually. So if you're using plain SGD, one of the conditions for SGD converging is that you gradually decrease the learning rate until it approaches zero. And under this condition, you can see that SGD is actually guaranteed to converge. So especially if you're using plain SGD, this is something you should be very aware of. Another thing to note, I think a lot of people know this, but if you don't know this, it can cause lots of problems for you. Each optimizer has a different default learning rate, and they are very different. So like for SGD, a common learning rate is usually in the 0.1 range, like 0.1, 0.4, 0.5, or something like that. For Atom, the learning rate is 0.00. The default learning rate is 0.001, and you often see it reduced a little bit or increased a little bit, depending on what you're doing. So if you accidentally use the Atom learning rate with SGD, SGD won't learn anything. It will just, continue, and your loss will never decrease. And if you accidentally use the SGD learning rate with Atom, training will explode, and you'll never converge. So. Are there any questions about learning rate or tuning learning rates or things like this? No? Okay. For initialization, oh, sorry, I forgot something one other very important thing. So another important thing that I don't even have on my slides is you need to be aware of the fact that there's gradient clipping. In gradient clipping, the basic idea of this is you calculate all of the gradients over all of your parameters, theta. And if after you've collected this is basically a large vector with all of the gradients. And the problem is for some models, like let's say you have a very deep model, let's say you have an LSTM. Sometimes these gradients can get extraordinarily large after backpropagating through lots and lots of layers of LSTM or things like this. And in order to prevent this from basically breaking training and making things explode, it's very common to basically take the L2 norm or the L1 norm of this, and divide the gradients overall by this norm times some value times t, where t is a threshold, if this norm itself is greater than the threshold. So it's like divided by equals if this is greater than t. Sorry, I have a strange mix of like Python and equations here, but basically this is something that you do. And some toolkits like Dynet do this by default. I believe PyTorch doesn't do this by default, right? Unless you turn it on. Can someone PyTorch? Yeah. So it doesn't turn it on by default. So this is something you should be aware of. It's good. T, you often set it to an arbitrary value like 5, and the good thing about this is this basically makes your gradients stay in the same range across your batches, across training, from the very beginning when you have really big gradients to the very end when you have much smaller gradients. Are there any questions about this? Yeah.
So previously you mentioned that for the vanishing gradient problem, you can use residual connection or highway networks. So when would you prefer one over the other?
So when would you prefer residual connections or highway networks? That's a good question. This is simpler. So like if you want to have a simple model or a simple method, this is definitely simpler. You just add in the input to the output, and this doesn't increase the number of parameters. Highway networks, I believe, seem to be a little bit more expressive. And basically what they're doing is they're saying you can decide whether you want to keep the input and pass it along, or you want to update something. So in order for a residual connection, something like a residual connection to be able to learn how to do this, it will need to be able to learn how to essentially cancel out the input in addition to sending a new input. So I feel like for some things, highway networks are more natural at modeling the fact that you want to update your features. But they do add this extra gating function that needs to be parameterized. So that might, not be as good any other questions? Yeah.
So the chemical paper for classification, it says you can scale down the weights of the projection layer in a similar fashion. So how would these two methods compare, flipping the gradient and scaling down the weights in terms of effectiveness?
Okay, so you can scale down the weights of the classification layer. I actually didn't read that carefully this time, so I don't. That's not included in our baseline implementation, is it, Junting? Is scaling down the weights of the layer, the Kim et al. In the Kim et al. Paper? I don't think we implemented that. Yeah. So, but anyway, my impression is that that kind of thing is more like regularization on the model to prevent overfitting, as opposed to making learning better. So like preventing the weights from getting too large is a way to prevent overfitting. And I'll actually talk about that in a second. But I don't remember that part of the Kim paper that well, so I'd have to go back and read it to give a completely definitive answer. Any other questions? Yeah.
Is there a situation that we could combine like several different optimizers together, like first you use them and then you use GD?
Oh, could you combine several different optimizers together to get a better result? That's a good question. Actually, there is precedent for this. I believe the original Google neural machine translation paper basically ran Atom first and then ran SGD afterwards. And the reason why they do this will become clear in a few slides, so I'll talk about it then. Yeah. Any other questions? Okay. So let me move on. So initialization. So neural networks are very sensitive to initialization. And the reason why is because they result in different size gradients and also different places on a nonlinear function being more common. So to give a particular example of this, let's say we have an affine transform followed by a CAN-H nonlinearity. So like the kind of most common thing that you see in neural networks. And the CAN-H nonlinearity looks like this, where x is 0, and then y, x is centered at 0, and then y is between -1 and 1. And depending on how big your weights are, where your outputs will fall along this function differs a whole lot. So for example, let's say your weights are very small. Most of the outputs will appear approximately in this area, right? They'll appear approximately close to 0, which means your outputs will also be 0. Or if your weights are very big, most of your outputs will appear somewhere in the long tail, which means they'll be either 1 or -1. If you look at the gradient of the tan-h function, the gradient of the tan-h function looks something like this. So you have a gradient that's very close to 0 almost everywhere on the long tails, but when the input is around 0, your gradient is close to 1. So what this means is if all of your outputs are right near the middle, your your inputs to the next layer will be all around 0, right? Which is not a good thing. You don't have anything for the next layer to use to do its classification. So it'll be very hard to learn. If all of your outputs are very big values, the values will be 1 or -1, but the gradients will be very close to 0. So essentially, what this means is because your gradients are very close to 0, you won't be able to learn either, because you'll be, doing back propagation, all the gradients will become 0, and the earlier layers won't be able to learn from what you got from the outside. So especially for the tanh function, but also for other nonlinear functions, it's kind of important that most of your outputs are in a reasonable range. And this is one of the major reasons why initialization is very important in these cases. So standard initialization methods for parameters include things like Gaussian initialization, where you initialize with a 0 mean Gaussian distribution. Uniform initialization, where you pick a range and simply initialize uniformly within that range. And then there's variants of initialization, which include Glorat initialization, which is also called Xavier initialization sometimes, or He initialization. And what these do is they initialize in a uniform manner, but based on the size of the parameter matrices or whatever you have, they modify the range that you're sampling uniformly, so that the output is like this. There's actually a really good discussion of this in the deep learning textbook. There's a textbook, Deep Learning, by Ian Goodfellow and Yeshua Bengio and Aaron Corville, that discusses the various initialization strategies extensively. But this is actually really, really important. And when people go back to try to re-implement something and are having trouble, this is the biggest thing that people overlook as an important element to their re-implementation. So make sure you're very aware of this. So yes, are there any questions about this? Okay. The next thing I want to talk about is creating mini batches. And just as a reminder, when you're mini batching in RNNs or other kind of sequence-based models, you have to do stuff like padding, masking, etc. And one thing that we do is we group together. So we have to do padding and masking, etc. And one thing that we can do to prevent, padding and masking to have efficiency, cause efficiency issues, is if we use sentences of different lengths, we try to avoid this padding and batching masking, because it can result in slow training. So to remedy this, what we do is we sort sentences. So similarly length sentences are in the same batch. So for example, we would sort, source based on the length of the sentence, so that the short sentences are in the same batch, long sentences are in the same batch. One thing to be aware of, though, is that this can actually affect your performance. And actually, we had a question about this on Piazza 2, I believe. But basically, we did an experiment for sequence-to-sequence models where we tried various ways of doing the sorting and bucketing to make training more efficient. And the blue line is shuffle. The green line is when we do sort by the source side. The orange line is when we sort by the target side. The red line is when we sort by the source side length and then by the target side length. And the purple line is when we sort by the target side length and the source side length. And basically what you can see here is shuffling is slower unit time, because you do lots of padding and masking, which takes time and kind of wastes time. But shuffling actually gives you essentially more stable results, especially when you're using an optimizer like Atom. And this is the reason why is because basically if you're not shuffling completely randomly, you're kind of biasing the distribution of the sentences that you have in each mini batch. So you can be aware that this can cause performance issues. So this is all for kind of the training time issues. Does anyone have any questions or things like this? Yes?
So what kind
Well, what kind of thing will be influenced by this sorting and padding? That's a good question. I don't really know. I imagine it's any task where you have sentences of very different lengths, because then you would have lots of buckets of long sentences and short sentences and things like that. But I can't tell. We only ran it on sequence to sequence, so I can't tell for sure.
I feel like this was influenced the like sequence model than some other model like CMU.
That might be the case. So like one reason why you could say that is maybe the sequence to sequence model, one of its jobs is to decide what length the output should be. And because of that, if you're giving it things of wildly different lengths in different mini batches, that would fluctuate a lot. But I can't say that it wouldn't. I can't say for sure that it wouldn't affect text classification or like tagging or something else. I bet it would still have some effect there. Okay. So the next thing, this is debugging at test time, and specifically debugging at test time for structured prediction or sequence-to-sequence models. This is the most common mistake that people make. This is the most common way to introduce bugs into your program when you're creating a model for NLP. And the reason why is because usually your loss calculation and decoding or generation will be implemented in different functions. And specifically, if you look at the encoder-decoder example that we have on the class website, there's the calc loss function and the generate function. The calc loss function calculates the loss for training, and the generate function generates sentences for testing. And the reason why is because calc loss is usually like a mini-batched function. It's usually calculated. It's usually calculated over multiple sentences at the same time for efficiency purposes. You don't actually need to generate any outputs. You just need to use the ground truth and feed it back in. Whereas when you're decoding or generating outputs, for example, in an encoder-decoder, you need to do things like beam search. You need to add an argmax into your calculation, which you wouldn't normally have in your calculate loss function. So basically, because these two processes are quite different, you more or less need to implement them in different code. And like all software engineering, duplicated code that's doing essentially the same thing in different functions is a source of bugs. And in particular, if the scores that you're calculating in the generate function here don't match the ones in the calc loss function, this means that you'll be generating something other than what your model was trained to generate. And this can cause major problems. So a first thing that you can do is, because generation is usually not mini-batched, but training is, the first thing you can do is make sure your mini-batch code matches your non-mini-batch code. And there's a very easy way to do this. What you do is you calculate the loss with a large batch size, let's say 32, and then you calculate the loss for each sentence with a batch size of 1, so individually, and then you sum them together. And the value should be basically the same, modulo like numerical precision issues that you get because you're calculating floating point numbers. So basically, you do the first one with tensor multiplications, etc. You do this one by just writing a for loop through all the examples, and you can check that they're the same. And unlike a lot of things in neural networks have like lots of randomness. We don't actually know. We don't have any guarantees about neural networks because it's a non-convex optimization problem. We're using stochastic gradient descent, so the loss isn't guaranteed to go down every time. But in this case, we can actually create a unit test, and we know that these numbers should match. So this is very easy to do, and you can implement this as a unit test in your code and make sure everything's working. You can also do this for your CNN that you're implementing now, or whatever, for text classification. So you calculate the loss function for the size 32 mini batch, and also for each sentence individually. Another thing that you can do is debug your decoding or your sentence generation if you're doing something like a sequence model. And the key here is that when you're doing decoding or sentence generation, you're essentially calculating the likelihood of the output, right? You know, you're trying to find an output that gives you a good likelihood or a high probability. So within your decoding code, you'll be searching over various things. You'll be calculating which one has the highest probability. So in the end, you'll get an output and you'll get a probability for that output. So the nice thing here is that probability should be the same probability that your calc loss function is calculating, right? It should be, you know, exactly the same thing that you get from your calculate loss function. And the way you can test this is by, actually I'll skip this because there's actually an easier way to do this. You can just ignore this. What you can do is you can run your generation code, generate an output, and then calculate the loss of the output. And that loss should be exactly the same as the thing that was calculated by your search code. Are there any questions about this? Is this clear, or can I clarify anything? Okay, I'll continue. So another thing is, you know, one way we can do search is greedy search, where we just, you know, take the top one decision at every time step, which I believe is what is implemented in the encoder-decoder example. But a more effective method for search is beam search, where we basically, instead of picking one high probability words, we maintain several paths through the output. And I talked about this in a little bit in earlier classes, I believe. But one problem with beam search is it is somewhat complicated, so it's possible to make mistakes in implementing this. So another example of how we can debug in this case, and actually write a unit test to debug, as you make the beam larger, as you search over more hypotheses, the model score or the probability of the output that you find should get better almost all of the time. So what you can do is you can run search with varying beam sizes and make sure that the output that you find with a larger beam size gets a better model score than the output that you get with a smaller beam size. And you can also create a unit test testing this. And actually, maybe I can show, we have a, we have an MT toolkit, which apparently has a potential security vulnerability, which I should go fix. We actually have tests for this, where we implement all of the things that I just talked about here. So we have like the test beam search thing that tests whether greedy search produces the same output as beam search when the beam size is set to 1. We also, I believe in some other place in the code, have a test where we gradually make the beam size larger and make sure the score gets better. So this is very, very useful, and this will find bugs 10 times faster than than like trying to debug on your own on the actual outputs that you would be trying to process. Oops. Okay. Are there any questions about this? Okay. So finally, look at your data. I hope this should go without saying, but you know, sometimes you know, you get caught up in your BLEU score or your classification accuracy, and you don't actually go in and look at the data that you're processing itself. With respect to, especially to decoding problems, if you're generating output in a sequence model, very often you can kind of detect that something is wrong by looking at the output and seeing that it doesn't look right. One example that we had in an actual toolkit that someone was implementing is we had an off by 1 error when we were generating our outputs and actually writing them out to a file. And in this case, basically, we dropped the first word in every sentence. So if you looked at our output, the output looked really nice and fluent, except it was missing the first word for every sentence. And this is something, our blue score was pretty good. It was like 2 points worse than we expected it would be. But if you looked at the output, immediately you saw that something was wrong, basically. So this is one thing you can do. A more kind of funny example, I actually don't remember exactly how we found this, but we had a system that was training a large-scale language model, and we realized the vocabulary didn't match the vocabulary we expected, and realized our system was accidentally turning the abbreviation for University of Nebraska at Kearney, which is UNK, into an unknown word. So this is another thing that probably you could not find by just looking at your loss function, right? Another thing you can do, so this is kind of like a qualitative way to analyze your results. Another thing you can do is quantitative analysis, and this is also really useful. So what you can do is you can measure gains quantitatively in a more fine-grained manner. So for example, what is the phenomenon that you believe your model should be doing well at or not doing well at? And is this getting better? So an example is, let's say you came up with a model that was supposed to do better at low frequency words or classifying sentences that had lots of low frequency words or something like that. You can specifically look at accuracy on something like low frequency words and see if it's increasing. Let's say you have a syntax-based model and you expect the syntax-based model to work better on things where you have long distance dependencies or something like this. So you should try to evaluate this. Or maybe you focused on search. And when you focus on search, you should be reducing the number of search errors as your search algorithm gets better. So the scores of the hypotheses you're finding should be getting better. So we have an example of this. This is a toolkit that we just released. I've told some people about this. Specifically, this is for quantitative analysis of things like language generation, where you're generating text and machine translation or dialogue response generation. And it calculates aggregate statistics about accuracy of particular types of words or sentences and finds salient examples. One thing I want to emphasize here is this is not something that works only for sequence models. Our toolkit is something that was designed for sequence models, but this type of analysis can be used for any task that you're interested in. So if you think about a task and say, hey, I'm not interested in language generation, and you can think about like what kind of parallel examples you could come up with. So I have an example of this here. And this is a toolkit called Compare MT that you can download if you're interested. But what I want to show is what kind of output it generates. And the way we generate this is we had a phrase-based machine translation and a neural machine translation system. We calculate the blue score for both of them, which is kind of the overall metric that we're interested in. But in addition to this, it calculates the accuracy of generation of words by their frequency. And you can see that the phrase-based machine translation system is better for low frequency words, whereas the neural MT system is better for high frequency words. You can also calculate the accuracy of words by part of speech tag. So you can see that the phrase base is better at nouns. The neural MT system is better at like connectives and determiners and other function words. And actually, interestingly, you can see the phrase-based system is better at base form verbs that aren't conjugated, and the neural MT system is better at conjugated verbs, which was kind of interesting to me. Other things it can do is it can calculate the accuracy by the type of sentence. So this is the accuracy by the length of the sentence, and we can see the neural MT system in orange is better at shorter sentences, where the phrase-based system is better at longer sentences. This is something you could also do for text classification, for example. It also calculates the difference between the generated in length between the generated output, et cetera. It also picks out specific n-grams that the system was better at generating than the other. And it basically counts up the different types. So I don't want to go through all of this. You can go back and take a look at like examples of what the toolkit can generate. But the important thing that I wanted to point out here is that these sort of aggregate, fine-grained statistics calculated over the whole corpus are things that you can calculate for basically any task that you might be interested in, even if it's not language generation. Are there any questions about this part for clarification? So the next thing I want to go into is battling overfitting, and this is hard. There's no clear way to do this. If we knew how to fix the overfitting problem, we will have solved machine learning, and we can all retire. So you know, I'm not going to give any fixed answers here like I did for the previous ones. But what I can tell you is I can tell you how to diagnose it. And once you've diagnosed it, at least you know you need to be doing something about it. So the symptoms of overfitting are that the training loss converges well, but the test loss diverges. And interestingly, here for the case of overfitting, you still really don't need to think about the test accuracy or the test blue score or anything. It's fine to just still think about the loss. Because the difference between loss and accuracy is something that you can think about from a different framework. So if you just ignore the accuracy here, despite the fact that I said you could ignore accuracy, I still accidentally put it on the slide. So, but ignore that. But what you see here is the training loss is going down. This is the red line here. But the test loss, the development loss goes down for a little bit, but then it goes up again. And you can see it's overfitting. One thing to remember when you're worried about overfitting is that with a sufficiently large neural network, it's basically possible to memorize your training data. So your neural network has more parameters than training examples normally. Normally your neural network has, you know, hundreds of thousands or millions of parameters, and very often you won't have that many training examples in your input. And even if you do things like randomly shuffle the training labels, so there's no correlation between the input and the labels, it can still learn. So that's what this paper is showing here. You have completely random labels that are completely disassociated with the input, but after a few epochs, it is able to memorize the entire training data and reduce the loss to zero with sufficient capacity. Actually, there's kind of an interesting thing in this paper that tells you exactly how many parameters you do need to overfit the training data. Does anybody know how many it is? What is it?
It would depend on the training data.
It actually doesn't depend on the training data. Any ideas? It's a specific type of network architecture, but it's basically, this is almost correct. I might get a small detail or two wrong, but basically it's O of n plus d, where d is the number of dimensions in the input, or the input plus the output or something like this, and n is the number of training examples. So basically, like if you have 100,000 training examples and your input classes are 50, your output classes are 50, you need 100,100 parameters to memorize it. And the reason why you can do this, just to give an intuitive explanation, is essentially you can project all of the input onto a line. And then after you project it onto a line, you can basically create rectifiers, rectified linear units, ReLUs, that split each training example into a different bucket. And then based on the different bucket, you can assign each bucket to the appropriate labels. So it's kind of an interesting result. You can go back and look at the results here. So you need a shockingly small number of parameters to memorize your data if you have the right neural network architecture. Of course, this would never generalize to new examples. This would never work. So, on your test set, which is why we still need to think about design architectures. So a second thing to know about overfitting is that adaptive gradient methods like Atom tend to overfit more. There's a nice examination of this in Wilson et al. 2017. This examination that they do here doesn't 100% agree with my experience, but I think it's still a nice paper to read anyway. And basically, what they show is that when you carefully tune the learning rate, et cetera, for all of these various methods, actually SGD tends to do best in terms of generalization accuracy, and things like Atom tend to be much more likely to overfit. So that goes back to the question that we had much earlier in the class, which is, would you want to mix together two different optimizers? And the answer to this is maybe yes, because SGD is a very slow learning method. It takes a really long time to learn in many situations, whereas Atom tends to converge much faster. So what the Google neural machine translation paper did basically was they trained with Atom for a couple epochs because Atom is very fast and it gets you to a good place. But then they continued training with SGD in the end to help prevent overfitting. So this is something that you could do. You could probably come up with a much nicer method of doing this than just like switching between two optimizers. But it is something that people have done.
Where do we exactly draw a distinction between our data is small or it's adequate enough?
So there's no threshold for small versus adequate, I guess. The more data you have, the better, very often. So I don't know if that was the question you were.
So I mean, like,
yeah.
when you're working on a problem, like a lot of things depend on the size of the data. So how do you know that this was like I should use this optimizer for this data size? And, like,
Oh, I see. Okay, yeah. Well, so that's a good point. So that goes back to diagnosing overfitting. So if you see that your training loss is much lower than your development loss, then that's a symptom that you're overfitting. So you might want to consider this. If you see that your training loss and development loss are virtually the same, then you probably don't need to worry. And if you see they're both decreasing with a similar curve, et cetera. So, any other questions? Yeah.
Is there any intuitive explanation as to why adaptive gradient can overfit more than experimental?
Is there any intuitive explanation? Yes, there is an intuitive explanation about why adaptive gradient methods tend to overfit more. The reason why is because adaptive gradient methods, the whole basis of adaptive gradient methods is that they very aggressively update rarely used parameters. So because they're very aggressively updating rarely used parameters, it makes it much easier for them to essentially memorize the training examples with like rare vocabulary or things like that and kind of latch onto that over all of the other evidence that's present in the sentence. So for like text classification, it sees one example with the word hippopotamus, and that was a highly positive training example. It will remember very quickly that hippopotamus is a high sentiment word, even if that's not the case. Whereas SGD would not update hippopotamus much, and it would rather just update all the other words in the sentence, which might be, might be more generalizable. Yeah. Any other questions? Okay. So ways you can prevent overfitting. So this is just a reminder. Neural networks have lots of parameters. We want to prevent them from overfitting. We can do this by monitoring our performance on held out development data and stopping training when it starts to get worse. It also sometimes helps to reduce the learning rate and continue training. So this actually goes back to the question of what is the function of reducing the weights that we had before. So if you're reducing the weights of the parameters, what this is doing is it's helping prevent the parameters from getting really big and making your estimates overconfident or overfit to the training data. And early stopping also has a similar effect. If you're using stochastic gradient methods that do a limited number of updates, this also helps prevent the parameters from getting too far away from what they were at the beginning of training. So this also indirectly acts as kind of a regularizer to prevent the parameters from getting very far away from where they were at the very beginning of the training. So early stopping is kind of another way to do this. Reducing the weights would be another way to do this. Having an explicit regularizer over all of the weights so that they are close to zero, like an L1 or an L2 regularizer, would be another way to do this. So development-driven learning rate decay, we talked about this before, but just as a refresher, every time the development set accuracy gets worse, you reduce the learning rate maybe by half, and this is effective at helping prevent overfitting as well. Dropout, everybody should be using dropout. Basically it drops out nodes and helps prevent overfitting. It's one of the uniformly effective methods in neural networks that works almost all of the time. So this is something that you should be using in most of your models if you want them to work well. Okay. One other thing that I forgot to mention here, because overfitting, you can view overfitting from a kind of like machine learning perspective where it's just like better optimizer, better regularization, et cetera. But actually another very effective way to prevent overfitting is just come up with a better model architecture that generalizes well. So another way to help your model work better is to come up with a thing that makes it easier for the model to learn something that is consistent and generalizes. So overfitting is also, in a way, a symptom of your model not being a well-designed model. So it can give you motivation to work and come up with a better architecture for the problem. Okay. So the last part, this is a really important thing that I think a lot of people don't think about quite enough, but it's very, very important, which is that mismatch between the function that you're optimizing, your loss function, and the thing that you're evaluating, the evaluation metric. So the loss function is almost all the time in neural networks, maybe 98% of the time. We're optimizing something like maximum likelihood. But even though the likelihood is getting better, accuracy can get worse. And this is because likelihood is not, there's no direct connection between, there's a connection between likelihood and accuracy, but it's not a direct 100% monotonic connection between the two. I have an example of this. I don't like this example quite as much as the other one. So this is a good example. This is on the very, very simple task of MNIST sentence classification. MNIST image classification. And basically, the loss you can see is going down on the training set, but very quickly the loss starts to go up on the test set. Whereas for accuracy, the accuracy on the test set actually, or development set, actually continues to rise for many, many epochs. And this is a really, really common thing to see in maximum likelihood trained models. And it has an intuitive explanation. Does anyone have a guess what this intuitive explanation is? No? So it has to do with how confident the model is. So at the very beginning of training, the model, isn't confident at all. It basically predicts both of the classes, all of the classes with approximately uniform probability, which means that, let's say we have 10 classes. If we're talking about MNIST, that would mean that our perplexity would be 10. Because we have 10 classes, we have a uniform probability over them. As we start training, the model very quickly becomes confident in its predictions, and it might, be might think it's right about half of the time, which means its perplexity would reduce to, on the training set, would reduce to about 2. And then it gets more and more confident until it's basically 100% confident about its predictions on the training set. So that would reduce its perplexity to 1. And that's what you're seeing. I'm measuring log likelihood here, but if you can imagine this is perplexity, that's what you're seeing here. And very quickly it becomes extremely confident in its predictions, right? However, it also becomes extremely confident in its predictions on the dev set. But unfortunately, on the dev set, it's really, really wrong a lot of the time, right? It's saying with 100% confidence, I know this is a 7, when the answer is actually a 1. So because of this, you start to pay a really big penalty in the log probability of y equals 1 on these wrong examples. And because of this, your loss is actually going up. However, these wrong examples are still, very much a minority of all of the examples in the input. And as you continue training the harder examples, you start to get them, a little bit more right on the test set. So your accuracy can continue to go up. The only problem is that your confidence in your wrong answers is going up, which is why the loss is getting worse. So this is very, very common in kind of classifiers. So does anyone actually know the connection between the loss and the accuracy? There's a mathematical connection between the two for, let's say, text classification. No? Okay. It's actually the loss is related to the expectation of the accuracy. So if you integrate if you take the expectation according to the model over and then you have this is essentially the expectation according to the model probability, and this is a value that is 1 if the label is correct and 0 if the label is incorrect. If you take the log of this value, value and then sum it over all the examples in your corpus, this is your loss function. So essentially the loss is the expected accuracy, but that can be very different from the actual accuracy that you get. And this is what you report in your papers, right? You report your accuracy, you report your blue score. So while these are highly related mathematically, they're not the same thing. And these divergences can cause big differences. And an even starker example is the case of machine translation, where actually if you do better search, if you expand your beam when you're doing search, and you have a maximum likelihood trained model, the score, the blue score that you have, will go down severely as you do better search and get better probability of your outputs. And the reason why, with respect to machine translation or sequence models, is because if you train using maximum likelihood, the probability is the product of all of the probabilities of the decisions you make in the process of generating your output. And because you're taking a product over probabilities, each probability is guaranteed to be between 0 and 1. The more things the more words you output, the lower the probability of the overall sentence becomes. So if you search better and better and better, you start getting shorter and shorter sentences, and your blue score doesn't like short sentences, so you get a bad score. So this is another very real example, and it's so real that somebody actually wrote a paper about it, or wrote, I guess, 1/6 of a paper about it at least. So this is a really big problem that affects your outputs. Yeah.
Could it also be that you have the imbalanced sizes of the different classes in terms of number of examples?
Mm-hmm.
So that you have a very small number of examples for 7, which you always predict as 1.
Mm-hmm.
So on the overall accuracy, it still keeps going up, but because you're always wrong on the 7, the loss also keeps going up.
So could this be a product, or could it also be because of label imbalance? So label imbalance is interesting because you can think of another metric that handles label imbalance, like F measure, for example. So like, let's say you have a very small number of positive examples, a very large number of negative examples, and you want to basically calculate your accuracy in predicting the positive examples, because you don't want it to predict negative all the time, right? If you're creating a spam classifier or something like that. So F measure, basically what it does is it does the precision times the recall times 2 divided by precision plus recall, where precision is the number of true positives divided by did I say recall? Divided by positive labels, and then this is the number of true positives divided by system labels. But anyway, so this is a widely used measure, and this will further increase the divergence between your loss function and your and the final measure you're optimizing, because at least the loss is the expected accuracy, but with respect to F measure, it doesn't mean anything really. Like the loss, might be lightly correlated with F measure, but it's not, directly correlated. So if you have label imbalance and you use accuracy, it actually doesn't really matter that much. But if you have label imbalance and you're using a different metric like F measure, there will be a really big difference between your loss function and your outputs. So how do you manage this? The most principled way to do this is to use some sort of structured prediction technique. And we're going to discuss these, especially with respect to blue score or something. We're going to discuss these in future classes. But this is rather complicated. We have things like structured max margin training, minimum risk training, reinforcement learning, reward augmented maximum likelihood, et cetera. But a much simpler method is to do early stopping according to the evaluation metric that you care about. So according to accuracy or according to F measure or something like this. So if you remember this graph, we saw the loss was going down for a while, but the accuracy continued to go up. So what we do is we just perform early stopping based on accuracy. So instead of stopping our training here, where we get, or I guess here, where we get the best loss, we just keep on training until our accuracy doesn't get any better, and we stop where our accuracy gets the best. So this is something that you could definitely try. The one problem with this is actually accuracy tends to fluctuate more than loss. So if you stop, too early because your accuracy is fluctuating, this can hurt things overall. So it's probably a good idea to try, I don't know, 5 epochs or something like that first before you even start thinking about stopping or whatever. So just be aware that this can fluctuate more. So I have some final words with regards to debugging, and specifically reproducing previous work. This is particularly important because assignment 3 in this class is reproducing previous work. So your grade is directly dependent on how well you listen during this class. So reproducing previous work is hard for exactly the same reason why debugging neural networks is hard. It's because everything is a hyperparameter. If code is released, but you are planning on re-implementing the code, very often the only way to tell what was actually done is to look at the code and do this. And for assignment 3, you need to implement from scratch. So what I would suggest you do is implement it from scratch first and then go back and look at the code to verify any differences afterwards. If code is not released, good luck. Read the paper really, really carefully. When they say they're using uniform initialization with a range of 0.05, be aware that this is something really important. You know, all of the things in that little paragraph that describe all the hyperparameters are things that are really important. Which neural network toolkit they're using is also important. If they implement it in TensorFlow and you implement in PyTorch or Dynet, that could also make a mistake because Dynet does gradient clipping by default, but PyTorch doesn't. So, you know, that could make a difference. Another thing that people don't don't always think about carefully is that actually contacting the authors is a really good way to help resolve any questions you have. And people in universities are generally very helpful, especially if you email all the authors, not just the first author who may be away because, you know, she's in Hawaii enjoying the sun. You know, feel free to email all of the authors because it's all of their work. But another thing is, when you do this, make sure you introduce yourself. You don't just say, hi, I had a question. Say, hi, I'm a graduate student at CMU. I'm working on this for my research project, and I had a few questions. I've done this much. I have a few questions about like the details or something like this. And if people know you're serious about, you know, following their work, they'll be serious about replying to you. So this is a really good resource for you to use. Yeah, that's all I have for this. Are there any questions? Or? Yes?
So there seems to be a lot of things where things can go wrong.
Mm-hmm.
Is there some toolkit which can help us automate or lead us to the right direction while debugging?
Is there a toolkit that can lead you in the right direction for debugging? So that's a good question. There are things within neural network toolkits. I know both PyTorch and Dynet, for example, support printing out your computation graphs. They both support things like doing gradient checks, although gradient checks usually are fine because you're using a toolkit that has already done this as part of their testing procedure. But if you're manipulating the gradients in any way, you're doing an argmax anywhere in your network, this is something that you should be thinking about. Some things, yeah, I don't know if, that's a good question. If somebody knows this, you know, you could raise a hand and explain about it. Another thing is if you want help tuning hyperparameters, there are libraries for random search or Gaussian optimization of hyperparameters or stuff like this that you can use. But that's kind of a last resort, you know, like to get a little bit more accuracy, and it won't fix fundamental problems in your models. Yeah?
So TensorFlow has toolkits like TensorFlow, does that like
everyone, could you quiet down for a second while we finish the questions? So TensorFlow has toolkits like TensorBoard that help with visualization. I'm sure that might help too, but I haven't been super successful at getting visualization to help me debug anything. So, you know, maybe not. Any other questions? Yeah.
This is with respect to the assignment. The development set in the assignment is missing in like 4 labels. So I just wanted to know whether that would affect the development set accuracy, because we'll be looking at that while fine-tuning our parameters. So should we like resample some examples from the training set, or like how should we go about it?
Oh, the development set is missing some examples in the assignment. I just used the development set. The test set was created according to the same procedure as the development set. It might have more labels, it might not, but the test set is the same procedure. If you do cross-validation on the training set, that will give you a very different result. Somebody noticed that you get very high accuracies. The reason for this is because the training, development, and test sets are split by documents. So multiple sentences from the same document are included in the training set. So if you just do cross-validation, it will be a much easier task. So, yeah. Any other questions? Okay, I'll finish up then. Thanks.